Good morning, students. Welcome to online lecture series of discrete mathematics. Now, today we will cover our topic, that is equivalence relation. So, what is this equivalence relation? So, relation R on set A is called an equivalence relation if it satisfies following three properties. First, a relation R is a reflexive. Second, a relation R is a symmetric. And third, relation R is a transitive. So we know the reflexive, that is whatever elements belongs to the set A, right? Right? So that all the elements are related to self in a relation, and can say reflexive relation. Same in symmetric, if A is related to B, that is A comma B is belongs to R, then B comma A, or you can say B is related to A in relation R. For transitive, if A is related to B, B is related to C, then A is related to C is also belongs to the R. So if these three properties are satisfied by any relation, then we can say that the given relation is an equivalence relation. See the example. Let A is equal to, right, containing the elements 1, 2, 3, and 4, and R be the set. So R be the relation on this set A. Right? So we have to show that whether this given relation is a equivalence relation or not. Right? So first of all, so we have to find out whether given relation is reflexive or not. So for reflexive, right? So you have to check how many elements are in a set A. So in set A, there are 4 elements, that is 1, 2, 3, 4. So all these 4 elements relate to self in relation R. That is 1, 1, 2, 2, 3, 3, and 4, 4. R belongs to the R. So here, check that whether this 1, 1 is belongs to the R. Yes. 2, 2 belongs to R. Yes. 3, 3 belongs to R. Yes. 4, 4 also belongs to R. So this given relation is a reflexive relation. Second, symmetric. So for a symmetric, right? So relation R is symmetric when A comma B belongs to R, B comma is also belongs to R. So check in the relation. There is 1, 3 is here, 3 comma, yes, that is AB, BA. Again 4, 2, 2, 4 is also belongs to R. So we can say that this relation R is a reflexive relation. Then third property, that is transitive. So relation R is a transitive because A comma B, B comma C belongs to R, and A comma C also belongs to R. That is this 1 comma 3, 3 comma 1. That is your A, B. This is your B, C. Then A comma C is what? 1 and 1. So this 1 comma 1 also belongs to R. Again same 2, 4, 4, 2. So 2 comma 2. So this 2 comma 2 also belongs to R. So this R is reflexive, symmetric, and transitive also. So we can say that this R is an equivalence relation. So next. So after this equivalence relation, so you have to remember two things. First, if R1 and R2 are equivalence relation, then whatever their intersection of this R1 and R2 is also an equivalence relation. The second thing, if R1 and R2 are equivalence relation, then R1 union R2 may or may not be the equivalence relation. So intersection for the two relation, right? If these two relation R1 and R2 are equivalence relation, then intersection for these two are always equivalence relation. But for the union for these two equivalence relation, that is R1 and R2, may or may not be equivalence for your union. Next, inverse relation. Let R be any relation from set A to B. Inverse of R is denoted by R inverse, is a relation from B to A, which consists of those order pairs which when reversed belongs to R. That is R inverse is equal to B comma A, containing the pair B comma A such that A comma B belongs to R. Means here, that is, we'll see an example. Suppose set A is equal to 1, 2, 3, B is equal to X, Y, Z, and R with the relation from A to B, and this R equal to 1Y, 1Z, 3Y. So what is R inverse? So in R inverse, right, whatever pair is given, this is 1 comma A, right? So whatever relation from A to B is here, right? Relation from set A to B in R inverse is relation is from B to A. Means if a pair 1 comma Y is present, in R inverse Y comma 1 is present. So here for R inverse 1 comma Y, Y comma 1, 1 comma Z, Z comma 1, 3 comma Y, Y comma 3. Means here whatever first element is, first element gets your second element and second elements get your first elements, right? So here we have to again remember two things, that is domain and range of R inverse. Domain and range of R inverse is equal to range and domain of R. Second, if R is an equivalence relation, then R inverse is also an equivalence relation. Next, partial order relation. So a relation or R on set A is called as a partial order relation if it satisfies three properties. First, the relation R is reflexive. Second, R is anti-symmetric, and third one is a transitive. Right? Same in equivalence relation. Right? In equivalence relation, you have to satisfy three properties. First is reflexive. Second one is symmetric, and third is transitive. And for partial order relation, reflexive, anti-symmetric, and transitive. Only difference is in equivalence relation, you have to satisfy symmetric, and in partial order relation, you have to satisfy the anti-symmetric relation. Right? So in a partial order relation, we see the example. Show whether the relation x comma y belongs to R. If x is greater than or equal to y, is defined on a set of positive integers, is a partial order relation. So means here whatever set is given, right? In that set, a pair x comma y is present, right? This pair x comma y belongs to R if first element is greater than or equal to the second element. So suppose here this set A containing a 1, 2, 3, 4. Right, there are 4 elements. So here we have to find out the relation R, right? So what is the definition for this relation R? Is the first element is greater than or equal to the second element. X is greater than or equal to y. So here for this first element, so this 2 comma 1, that is 2 is greater than 1, 3 comma 1, 3 comma 2, right? This 2 comma 1, 3 comma 1, 3 comma 2. Again 4 comma 1, 4 comma 2, 4 comma 3. That is first element is greater than second element. Again first element greater than or equal to, right? So for equal to, again 1, 1, 2, 2, 3, 3, and 4, 4. So this is your R. So here You have to satisfy. This is your R, right? So here we find out the R, right? Right? Here we have find out R. Then we have to satisfy. So we have to find out whether these three properties are satisfied by this relation R or not. So first is reflexive. So with the reflexive, yes, because this is equal to x is greater than or equal to means here all four elements, that is 1, 2, 3, 4, is related to self in relation R, that is 1, 1, 2, 2, 3, 3, and 4, 4, right? So the relation R is a reflexive relation. Next, second property is that is anti-symmetric. The relation is anti-symmetric as a comma b comma a belongs to R. We have a is equal to b. So here we have to remember just relation is not anti-symmetric, right? Relation is not anti-symmetric when a comma b and b comma a also belongs to R. Here, right? Here this 1, 1, 2, 2, 3, 3, 4, 4. This satisfies this a equal to b. But here to remember this 2 comma 1, 1 comma 2 is belongs to R, no. 3 comma 1, 1 comma 3, no. 3 comma 2, 2 comma 3, no. 4 comma 1, 1 comma 4, no. 4 comma 2, 2, 4, no. 4, 3, 3, 4, no. So only one pair is present here. So as per our definition, two pairs, that is a comma b and b comma a belongs to R, and a is not equal to b. Then and then only we can say that this relation is not an anti-symmetric. But here such condition is not present, right? So we can say that the relation is anti-symmetric because a comma b comma a belongs to R. We have a is equal to b. Next, transitive relation. The relation is a transitive as whenever a comma b and b comma c belongs to R, then we have a comma c. So that is 4 comma 2 belongs to R and 2 comma 1 belongs to R. So AB, this is A, B, this is B, C, then AC, that is 4 comma 1 also belongs to R. So as the relation is reflexive, anti-symmetric, and transitive, then we can say that it is a partial order relation. Next, partial order set. You can say there is a poset. A set together is a partial order relation R on set A, and it is denoted by in bracket A comma R, is called a partial order set or a poset. Next is equivalence class. What is this equivalence class? Consider an equivalence relation R on set A. The equivalence class of an element A belongs to A is the set of elements of A to which the element A is related, and it is denoted by this equivalence class is denoted by in square bracket, right? So it is square bracket A. If you have to find out the equivalence class of element A, then you have to write down that element in a square bracket. So in the example, let R be an equivalence relation on set A, right? This set A containing 4, 5, 6, 7 defined by the relation R. Is 4, 4, 5, 5, 6, 6, 7, 7, 4, 6, 6, 4. So determine its equivalence class. So what is this equivalence class? As per the definition, if the element A belongs to it and is a set of elements of A to which the element A is related. Suppose this is a set A that is containing the elements 4, 5, 6. So here the element 4. So 4 is related to how many elements, right? So we have to find out that set. Same 5, this is 5 element. This element 5 is related to how many elements? 6, same 6. 6 is related to how many elements? This is the class of that 6. Same 7. 7 is related to how many elements? We have to find out. And this is nothing but the equivalence class for that each element. So find out. So this 4. So 4, see here, 4 is related to, wait a minute. This 4 is related to 4. Again, 4 is related to 6. So in equivalence class of 4, there are two elements, 4 and 6. Same for 5. 5 is related to 5 only, right? 6. 6 is related to 6 and 4, right? Means here, when we consider this 4, right? This 4 is related to 4, 6. Again, this 6, this 5 is related to only 5, and 6 is related to same, this 4 comma 6. So 4 and 6, and this 7 is related to 7 only. So this 7 is equal to 7 only. So here this 4 and 6 have a this 4 and 6 containing the same element. So we can say that this is equal to your 6 also. To 6 also. But same element 4 comma 6, 4 comma 6. So this is an equivalence class. Remember here this equivalence class, there is a rank is there. So how to find out the rank of the equivalence class? So number of distinct equivalence classes. Number of distinct equivalence classes is the rank of that equivalence class. So here, right? So in this equivalence class, right? So here 4 is 4 comma 6, 6, 4 comma 6. So this is one equivalence class is there, this 4 and 6, right? Distinct means what? That is different. So this 4 and 6 have same equivalence class. 5 is again different, and 7 is different. So this is one, this one is a second, and this one is a third. So there are 3 distinct equivalence classes are here. So so rank of this equivalence class is a 3, right? Rank of this equivalence class is 3. So we stop here. In next session we'll see the next topic.